Floor is yours.
Thanks, Yang. I'm glad to have this opportunity to introduce our work related to integrated CO2 capture and utilization. So it's a relatively, I think, new concept regarding the integration or combination of these two technologies, carbon capture and CO2 utilization. So my name is Dr. Chunfei Wu. I'm from Queen's University of Belfast. So my talk will include some background, recent progress, and in terms of using different dual functional materials, and then the conclusion and acknowledgement. So some background, I think we kind of all understand or kind of agree the requirement to capture CO2 to reduce CO2 emissions. That is mainly because of the human activities cause increase the CO2 concentration in the atmosphere and cause the climate change issues. So the main reason is the use of fossil fuels. So although we are developing renewable technologies, use renewable energy or other kind of energy, but I think the use of fossil fuel is inevitable in the short term, also in the middle term. So that means that carbon capture is necessary to remove carbon dioxide from different kind of sources. So it not just reduce CO2 emission, but also provides the economic opportunities to to capture CO2 and also to utilize the CO2. And of course, this will contribute to the climate change mitigation. So there are many technologies of carbon capture. I think mainly categorized as these three categories. So we have the pre-combustion. So that means we remove carbon out of the carbonaceous feedstock and produce hydrogen, because the use of hydrogen is CO2 emission free. And then oxy-fuel combustion. So oxy-fuel combustion, we use oxygen for the combustion directly, which produce carbon dioxide and water. So after the remove or condensation of water, the carbon dioxide can have very high concentration. So CO2 capture process basically is, in this case, is the purification of CO2 concentration. So we want to increase the concentration of CO2 from different sources, like from the 400 ppm in the atmosphere, or from 10–15% from the flue gas to nearly 100% of CO2, because that kind of CO2 will be used for transportation for CO2 utilization. I think currently a lot of research mainly focus on the post-combustion CO2 capture. We mainly capture CO2 from the flue gas. There's different technologies. I think the state of the art technology is use the amine solution to capture CO2. That there's a few commercial plants already available. But of course, the amine solution technologies, there are also challenges, such as high energy input and the corrosion of the ammonium, and also the other issues. So of course, using solid solvents like using zeolite, MOF, biochar to capture CO2 is also popular. One of the most popular CO2 adsorption technologies, calcium UP, use calcium oxide. So there's also other membrane-based CO2 capture. So other technologies also contribute to CO2 capture is like direct air capture. We capture CO2 direct from air. And so one of the questions is what we are going to do with the captured CO2. We can utilize it. We can convert the captured CO2 into different products like fuels, chemicals, and some materials. And in this case, we can, for example, convert the captured CO2 into methanol, CO, methane, and so we can also use CO2 directly as a dry ice. Of course, we can also store CO2, so we call it CO2 capture and storage. But in this presentation, I mainly want to focus on the CCU, CO2 capture and utilization. And conventionally, we capture the CO2 and we regenerate the solvent, produce pure CO2, and we might have CO2 transportation and storage, and before we convert the CO2 into different products. So in general, this conventional CCU process has a few steps and a very high, need a lot of energy, and especially when we use solvent, like solid solvent, or have solvent attrition issues. So there are many issues there. This challenge also materials. You need a catalyst, need a solvent for CO2 capture, need a catalyst for CO2 conversion. There's massive amount of research activity there. So in this case, in this presentation, we want to introduce this integrated CO2 capture and utilization. We call it ICCU, or some groups call it integrated CO2 capture and conversion, ICCC. So in this case, we only use one reactor, and we in the presence of dual function materials, which have two functions: is catalyst and also a solvent. So the solvent, for example, we can use calcium oxide as a solvent when we introduce flue gas, so that the CO2 will be captured in the reactor. And when the solvent saturated, or when the carbon capture stage finishes, we switch off the CO2 source. We then switch on the reducing agent like hydrogen. So the hydrogen introduced and will react with the captured CO2 directly and produce a product. So in this case, everything could happen under in one reactor, also possibly under the same temperature. This is this is novel and also provides many advantages. First is the same temperature. We understand that for CO2 adsorption, we have the capture, and normally the regeneration of the solvent need to be at a higher temperature. So for example, for calcium looping, the CO2 capture is around 550 and the regeneration is around 800 degrees C. So you need to heat this material up to the 800 degrees C, and then you cool it down to the capture temperature. So there's temperature looping there. And in most of the cases, the fluidized bed will be used because the materials can be transferred between two reactors. So if we use this concept, ICCU, we can use one reactor, fixed bed reactor, to simplify the process. And most importantly, if we reduce the reaction energy for solvent regeneration, we also reduce the energy input. Another advantage, which I'm going to talk a little more later, is we actually change the reactions, change the mechanism of reactions. So we also reduce the steps of CCU. So conventional CCU have CO2, have solvent adsorption, and also CO2 transfer, CO2 storage. And here, just one reactor. So as I said, this is a relatively new area. And we need a dual function materials, which has two functions: catalytic function and CO2 absorption function. So we also need a catalyst. What kind of catalyst we want, and how are we going to combine the catalyst and the solvent? And then the temperature. What kind of temperature we want? So because the solvent has different solvent works at different temperatures, like high temperature solvent, calcium oxide, maximum oxide, magnesium oxide works at around 300. Or if we use MOF biochar, that works normally at a room temperature. And what reducing agent we're going to use? We can use hydrogen to do the CO2 hydrogenation, or we can use methane to do the dry reforming. What kind of product are we going to we aim to produce? So we can have CO production, methane production, or methanol production. And at the moment, most of the ICCU studies focus on the CO production and methane production, because these are relatively easier reactions. So some statistics about ICCU. I think, to our best knowledge, it's become popular from 2014. And recently, currently, I think there's just around over 100 journal papers, publications there. So a very small area. And ICCU, say, if we introduce hydrogen to produce carbon monoxide, that is ICCU integrated with reverse water gas shift reaction. So there's more papers about that, and some papers about ICCU and dry methane reforming. That means introduce methane to produce syngas. Also, the ICCU about methanation, so introduce hydrogen to produce methane. Some papers published in ES Applied Catalyst B, Science Advance, and also a few published in CJ. So many research unknowns, and also it's gaining increasing interest. We estimate that around maybe 15 key research groups in the world are active in this area. So some nice review papers. So this one is about ICC review papers published in Sustainable Energy Fuel. I think it has around 70 citations already. So another review paper is in Carbon Capture Science and Technology, so just recently published. So I'm going to give a little more details about our research progress on this ICCU. So in this specific example here, we have a few samples, dual functional catalysts, dual functional materials. We have calcium oxide and nickel loaded on calcium oxide, and cerium promoted nickel calcium oxide. So we did some routine analysis regarding the pore size distribution, and the XRD analysis. So these results, the TEM shows that the particle size is quite big for the material nickel calcium oxide, and for the nickel particles. When we introduce cerium here, the C and D, the particles are quite uniformly distributed. So that means the introduction of cerium actually improves the distribution of the material. So we did some further analysis in EDX to mapping to confirm the distribution of these materials. And this structure mainly is calcium oxide, porous calcium oxide. So we have two functions here. Calcium oxide provided the adsorption side for CO2 capture, and the nickel provided the catalytic side for CO2 conversion. This is a typical ICCU process in the lab. So we did this in the lab in a tube furnace. So when we introduce carbon dioxide, you can see that CO2 is captured, and then we introduce nitrogen, basically just purge the reactor. We remove the CO2 inside the reactor. Then you can see here, as soon as we introduce hydrogen is this blue line. Then we can see the red line here is carbon monoxide. So carbon monoxide produced as soon as we introduce hydrogen. Remember here we didn't change the temperature. So here the CO2 absorption is at 650 and purge with nitrogen 5 minutes, and then we need to introduce hydrogen here. That same temperature, 650. Here, by the reaction time is quite long, it's 70 minutes. But you can also clearly see that the CO production, CO formation completes here. Okay? So that means most of the captured CO2 actually has been converted. So we then, from the result, can see when we have nickel introduced, the CO production significantly increased. And then when we have cerium introduced as promoter, we further increased, but very slightly. And I think then we investigate the influence of temperature at 700 and 750. It's clear that when we increase the temperature, the reaction time is shortened from 70 minutes to 50 minutes and further to 20 minutes. So we can still produce the carbon monoxide. So we did some in situ FTIR analysis and to confirm the reaction intermediate. So we think the two routes for the CO formation, the redox and also the format formation as an intermediate. This actually shows the stability of the material and I think 20 cycles. So the first one is with calcium oxide without nickel calcium oxide without cerium. The second one, the bottom one, is with cerium. You can clearly see that the bottom one has very high stability, and after 20 cycles. So we did some further analysis. We assume that the first one without cerium oxide, the pores become blocked after a few cycles. From here, we can see from the porosity, and also the SEM. I think the first one you can see it becomes quite solid without cerium oxide loading. Also, the particle size changed. So this one without the cerium oxide That's the original fresh catalyst. But after 20 cycles, you can see the big particles is observed. But for this material, calcium, nickel, and with cerium, so you see before and after 20 cycles is very similar regarding the distribution of particle size. So we further investigate the distance between the active sites. So we said we have nickel there and we have calcium oxide there. So what's the influence of this, the distance between these on the ICCU performance? One of the key reasons why we did this research is we understand during the carbon capture stage, like calcium oxide will become calcium carbonate. So the volume will become bigger. So that could actually encapsulate the nickel particles. So to stop the nickel particles for the catalytic reactions. So then we have the one-part materials preparation, we also have the physical mixing, and we also produce the calcium oxide first, then we load nickel, and we could also produce a nickel cerium oxide catalyst, then physically mix with calcium oxide. So in this case, the distance between this catalyst, between the catalyst and the solvent are quite big in micrometer scale. So we did some XRD analysis. So this one is mainly for, we also see methane produced, methane and CO. So it's clear here, the physically mixed material has a quite high CO2 capture and also the conversion, the production of CO and methane. So that means the distance needs to be long enough in this case. And we have this one. So first we have calcium carbonate produced. That means the materials, the CO2 is already inside. Then we load nickel. So the material has quite a good methane production. But then the second cycle, as long as we do the second cycle CO2 capture, the methane production reduced because the nickel on the surface is actually encapsulated by the calcium carbonate. We further confirm that use this FIB, SEM, and also EDX analysis. So normally for the surface nickel, the nickel concentration on the surface is higher than in the center. So that's normal, like this one and this one. But if in this case, the surface nickel is almost zero, so there's almost no surface nickel. That means in this case, the surface nickel actually were encapsulated or covered by calcium carbonate, which confirms our assumption or hypothesis here. So we also did some in situ XRD to confirm the formation of calcium carbonate and the nickel, and also the redox between the nickel and nickel oxide, these reversible reactions. So not too much new information here, mainly because it's a way to form calcium carbonate and then reduce that to calcium oxide. So we did some further studies regarding user magnesium oxide, which is intermediate temperature solvent, which is around 350. This is mainly for the production of methane. So we use the ruthenium loading on the nanorod of cerium oxide. Then we tested the materials there, and the key information is that with the increase of ruthenium, we increase methane production, but with optimum ruthenium loading is required. And personally, I think I think this kind of reaction use very kind of expensive catalyst and produce relatively cheap material methane. So it's debatable. I think at the moment our main focus on syngas production, CO production, because we understand the production of the CO, the syngas can be easily converted to diesel, to aviation fuel, and use a commercial like fish chop process. So syngas is more valuable than methane. Also here, the format species, carbonyl species actually we confirm they are intermediates during the reactions. So we also further study the morphologies of this cerium oxide, its narrow rows, particles, nanocubes. And here, just I think we did 10 cycles. Just very interesting point is here. After a few cycles, like 7, 8 cycles, almost 100%, I think over 95% of captured carbon dioxide actually converted. That means the CO2 conversion is nearly 100%. So we understand in conventional cases like CO2 hydrogenation to methane, CO2 hydrogenation to CO, if you use a mixture of CO2 and hydrogen, it's almost impossible to have the 100% of CO2 conversion. So this conversion can be very, very high using the ICCU concept. So we also started try to reduce the size of nickel. This is a narrow cluster nickel particles. So we did some TEM analysis, and the results shows that it's quite stable. And the key thing is that the TOF, the methane yield in terms of the per unit of nickel is very high because we use very small amount of nickel. I think it's 0.5%. 0.5% nickel can produce really high amount, of methane in this case. So a very important, I think this is another step in our work. So conventionally, like for reverse water-gas shift reaction, it's compulsory to have a catalyst, like nickel-based, iron-based for the CO2 hydrogenation to CO. But using this case, they realize that, okay, probably we don't need a catalyst. Calcium oxide only might work. And at the beginning of this research, I think most of the researchers still have the conventional thought, okay, we need a catalyst. So that's why most of the work, I think they always use a nickel. Like even ourselves at the beginning, we use nickel-based, iron-based catalysts. And then in this case, we just use calcium oxide. So calcium oxide to capture CO2 and also calcium oxide as a catalyst to convert the captured CO2 to CO. Or the calcium oxide is not a catalyst, so it's still unknown. But anyway, the hydrogen can react with calcium carbonate directly with very high conversion. So we tested this at 3 temperatures here, 600, 650, and 700 degrees C. So the first one is the red color is CO yield. So at 650, you can have about 2 millimole per gram of CO production. This unit, the millimole per gram per millimole of product per gram of sample, it's reasonable because we understand for MOF based materials, and the value is less than 1. It's about 1 millimole per gram of solvent. In our case, we could have, if we do this at 700 degrees, you have about 5 millimole per gram per solvent. So it's relatively high value. And then in the conversion stage, basically the process is we just put calcium oxide there, and we introduce carbon dioxide, and then we switch the carbon dioxide to hydrogen. So interesting that when you introduce hydrogen, very high yield of CO produced. And the conversion here is about 80, almost 80%. So that means 80% of the CO2, captured CO2, converted to CO, which is actually about the thermodynamic limitation of CO2 hydrogenation. We understand that for all the reverse water-gas shift reaction research, the conversion of CO2 is limited as 65% or less than 65%. And we also did some Aspen simulation because that is mainly the thermodynamic limitation. In this case, using the ICCU concept, because the CO2 source, the CO2 is not come from the gas directly. CO2 comes from the solid, comes from calcium carbonate. So the instant release of CO2 or the instant release of carbonate and CO2 absorbed CO2 or CO2 molecules. So there's unknowns there. So what's the form of CO2 react with hydrogen? But anyway, this can happen without catalyst, and that also make it simple towards commercialization because you don't need other metal-based catalyst, just a limestone. So we actually tested about 150 cycles. So you can see here at 600 degrees C, it's very stable, very stable. Even 650, it's the performance reduced for the first 20 cycles, 30 cycles, then it becomes also stabilized. We did some in situ spectra, in situ analysis, try to understand the mechanism, but it's quite challenging because one of the reasons is that it's quite difficult to observe the surface function groups because as soon as we introduce hydrogen, a lot of moisture or water produced that will actually interfere with the other signals. But we do find out that the water formation is very important during the CO2 hydrogenation process. You can see here from the gas analysis, the first 60 minutes have a lot of water produced, and that is related here. And then we have the hydroxy groups, and that mainly from water, hydroxy groups, and it can also react with calcium oxide. So that is the one we try to explore the reason behind, but it's still not quite clear at the moment. But anyway, I think the hydroxy group and the formation of water plays a key role in this process. Then we further studied the use of marble stone. Because calcium oxide, the limestone is working, but how about the marble stone? The marble stone also, because we basically use marble stone waste, is very low cost, and it can capture CO2. So here we have these typical cycles of CO2 capture, and introduce hydrogen, we can produce quite a significant amount of carbon monoxide. And we did a few cycles here, 5 cycles here. The conversion of CO2 even higher than calcium oxide. So it's 85% of CO2 conversion, and selectivity to CO is 100%. So it's very high. I think one of the reasons why compared to calcium oxide it has better performance is because in the marble stone there's other metals inside, like ions and also magnesium oxide. So we have current ongoing research about the marble stone to try to integrate the performance. So this is the 5 cycles. I want to emphasize that the use of pure hydrogen for the hydrogenation is very important. So the hydrogen concentration also has a big influence on this process. So using marble stone, we did about 20-30 cycles. Actually, the performance get a little bit worse after 30 cycles here. And that is mainly because there's a CO2 capture stage. So there's a sintering of the marble stone. But I think in this case, probably if we use, we can dispose the marble stone after 20 or after 100 or 1,000 cycles, like a limestone. These kind of materials can be used in the cement industry directly. So we don't have any other expensive catalyst in this process. So if we compare to other reverse voltaic acid reaction work, so like this one have nickel iron based and other nickel iron magnesium calcium, so quite complicated materials. We just use very simple marble dust and a marble stone. We can have quite a high CO2 conversion, like 85%, CO2 selectivity of almost 100%, and also the cycle stability is also quite good. The most important thing, our material, we estimated that is $20 US per ton, but it could be even cheaper than that. So it's quite a simple process using very simple material. We also did some further studies about the influence of the support, the addition of a promoter like zirconium oxide, titanium oxide, cerium oxide, and this result shows that at different temperatures, we do need a certain temperature to make the work, but the CO yield you can see here, using this calcium oxide solvent is actually the reaction temperature is limited by the type of solvent. So you can see at 550 is almost no reaction, no CO production. At 600 it becomes better, and the optimum temperature 700 degrees C for the CO production. That's, I think I mentioned a lot about the advantages of this ICCU concept using the calcium oxide or using the simple materials, but this is one of the disadvantages here, is the high temperature. So we need a 700 degrees C for this reaction. So that is one of the disadvantages. So, and then the research direction at the moment in our group is we try to bring down this temperature. So we can reduce the energy input. Then in general, these materials, cerium oxide have a better performance than other metal promoted dual function materials. So then another concept is we have dual looping. We can have calcium oxide, which is a calcium looping. We can also have iron oxide as a chemical looping. So we call it the calcium and chemical dual looping. In this case, integrated with ICCU. So we did some experiment, some calculation, traditional calculation to confirm the presence of the metals and the presence of the calcium carbonate, and also most of important is the calcium iron oxide. This material, we're going to talk a little more about it. So some immediate mapping confirms the wear distribution of the materials. So in terms of the performance, the first one, the top layer is nickel-based calcium oxide, and then the second one is iron-based calcium oxide. This one, the third row is nickel iron-based calcium oxide. The last one is the calcium oxide-based. So we can see that the iron-based material has better CO2 capture as CO production than the nickel-based. And the bottom one, although the capacity is quite high, the bottom one you can see the reaction, the kinetics or the reaction speed is quite slow compared to the top three in the presence of nickel and iron. And we did some XRD analysis. Basically, we take the sample out at different stages, and we do the ex situ XRD analysis. One of the key information here is we confirm that the calcium iron oxide is very important in this process, and it can react with reduced by hydrogen, produce calcium oxide iron, and also can be reduced by iron. So that is part of the iron chemical looping process, and it has a relatively higher CO production and also fast reaction speed. The other thing is for this process is when we have the nickel and iron produced in the CO2 utilization stage, we might have some issues at the CO2 capture stage, because in the CO2 capture stage, the carbon dioxide could be reduced by nickel and iron, and we produce carbon monoxide. We want carbon monoxide in the CO2 utilization stage, but we don't want carbon monoxide in the CO2 capture stage. If the flue gas is the CO2 source, so we don't want carbon monoxide in the flue gas. That means after the CO2 utilization, we can use nitrogen purge, steam purge, air purge. Basically, this is just to oxidize the nickel and the iron, or is any carbon left there, we can oxidize the carbon. So after the oxidation, during the CO2 capture stage, we will have much less CO production. So without this treatment, there's quite a significant amount of carbon monoxide produced in the flue gas. Of course, if the CO2 source is syngas, like from biomass classification, then we don't need to worry about this. In some cases, if the CO2 source is the flue gas, we need to consider the production of new pollutant in the flue gas. So I just want to have give you some ICCU resources. So we had the first ICCU workshop, because as I mentioned, the ICCU or ICCC is a relatively new area, and very few research groups. We have this workshop organized by Elsevier, and we have around 10 research groups give a very short presentation there, and then we had a panel discussion. So the video is recorded in there. And also we have the ScienceShare website, and it has a category of integrated CO2 capture utilization. We have category 2 under challenges, ICC integrated with dry reforming, ICC integrated with methanation, reversible gas reaction. Then category 3 is influence of temperature, solvent development, so mechanism. So a lot of information is there. Then I want to take 1 minute to introduce our journal. We developed the carbon capture science technology journal, which is IChemE journal, open access journal, published by Elsevier. And the journal is launched in 2021. And our aim is to become a top journal in the carbon capture research area. And we would like to see a first impact factor near 10 in 2024. So, for example, we already have almost 150,000 downloads, 6 issues published, 84 papers published in total. So we have submitted the SAI application in April 2022. We currently have a special issue with the 2023 IChemE Citizens Young Investigator Award. So in conclusion, the ICC, I think, is very promising material, concept technology, which can significantly reduce the energy requirement, also to simplify the CO2 capture and utilization process. And so, but the materials are very important, dual function materials, or just use calcium oxide alone, and also the promoters, the catalyst, the combination of catalyst and material and solvent, and also the reaction temperature are really important. So a lot still need to be done. And our idea here is try to simplify the process, because anything simple, it will be easy to commercialize. So try to use calcium oxide alone, limestone, marble stone, very simple materials to promote the technology. So I would like to thank my student Hongman, Xu Zhuang, and also collaborators, Professor Jun Huang from Sydney and Paul from Leeds, and also other collaborators from Manchester, and also Catalyst Hub and Cardiff University. Actually, and also the funding from European Union. Okay, thank you very much.
Thanks, Chunfei. Very interesting talk. I think it's a truly a smart idea, doing CO2 capture and CO2 conversion at the same time, also same temperature. So we're open for questions from the audience. I'm not seeing any questions in the chat box. So if you have any questions, just feel free to unmute yourself and speak out. You should be able to unmute yourself. I have already changed the setting a couple of minutes ago. So let me start with a couple of general questions. It's a very new concept to us. So my question is more about, the background part. So I remember at the beginning you said there are different ways to capture carbon. One of them is post-combustion. I understand that there's energy consumption involved to do post-combustion carbon capture. For instance, there's a huge push in the research area of electrocatalytic conversion, where you have to use electricity to convert. We all know such a thing exists, but we don't really have a concept how much energy would be consumed extra for this type of conversion. Is it really feasible or promising?
Yeah, thanks. Yeah, I think that's a good question. Always there's a question about the cost and energy requirement for CO2 capture and CO2 utilization. And we all understand actually CO2 capture is not going to be make profit, to be honest. So it will be one of the costs, maybe could be integrated in other processes, like in the power plant for the electricity production. I think what we want to do now is try to reduce the cost, And we could only compare our technology, we call ICCU, with the conventional CCU. So we actually, I didn't mention that in my report, in my presentation. We do have a paper about the economic analysis of these two technologies. So I think one of the key advantages in here is we will reduce the energy requirement compared to the conventional carbon capture. But as you said, this is actually is not going to make profit, and it always needs a lot of energy. It's also challenges to quantify this process because like ICCO, there's no pilot plant and no commercial plant. But this technology, actually, ICCO, there are some groups in China, they already received a lot of funding to start a pilot plant. So some demonstration plan could be available next year.
That's nice. I've got another question about the staging process of capture and conversion. So looking from your data, you always purge CO2 first and let it cool down and then start converting. I understand, it takes time to convert CO2 to a product. I'm just wondering if it's possible to do it in a continuous way. So you have your CO2 flowing in at the same time it's captured and converted and the product flows out. Is that even possible?
Yeah, that's a good question. So because in this case, we actually switching the gas between CO2 source and hydrogen. Mm-hmm. So the materials, we could use a fluidized bed or even fluidized bed mainly for the materials transportation. But normally we can use a fixed bed. Then we just switch the gas, and probably we're going to use a few reactors like to parallel working in this process. So when this reactor introduces carbon dioxide, that reactor introduces hydrogen, then we switch between these two to make it continuously working. Yeah, so it's not like conventional, the mixture of CO2 and hydrogen. So yes.
Yeah. So I think Rob's got his hand up. Rob, can you unmute yourself?
Can you hear me?
Yes, perfectly.
Oh, great. Okay. I just wanted to say what a nice talk. And thank you very much for this. Just following on, really, Young mentioned that the possibility of doing, capture and conversion of CO2 in a sort of continuous process. And of course, one of the issues there is, as you showed in your talk, is that the same conditions aren't necessarily ideal for both. You've showed how, you work towards trying to get the temperature sort of equitable, and presumably the pressure as well. I mean, these are all things that are important. But I guess also, what about the scale of how does that match up? Because when you're doing like post-combustion capture, you need really quite large quantities of sorbent, don't you? And I'm just wondering how that kind of matches up with what, how the catalysis is going to work.
Yeah, thanks, Rob. I think the first comment is very good. We are actually struggling to match the temperatures. So yeah, we have the capture temperature and the catalytic temperature. But actually, ICCO could be done at different temperatures. So it's already tried by the group in America, and also we also have tried it. So we do a carbon capture at lower temperature, then we increase the temperature and do the CO2 conversion. That's also fine. But maybe some CO2 will be released during the heating up process, and also you're going to need. And the things that I think the key thing ICCO, the advantage is actually change the reaction mechanism. So before it's a hydrogen and a CO2 gas reaction. Now it's hydrogen and the captured CO2 reaction. So the captured CO2 is actually in the solid form. So the instant release of CO2, that actually we can have a hydrogen to CO2 molar ratio, I don't know, 1,000. Instead of we have a conventionally hydrogen CO2 molar ratio is 4 or 5. So that changes the thermodynamics. And this is one of the advantages. And that's also why the hydrogen can react with calcium carbonate directly without any catalyst. And regarding the continuous scale, I think if you just use marble stone or limestone, we have a lot available. Just a big fixed bed, a few fixed beds there, and at the end of life, just through the marble stone or through the limestone to the cement industry. And then, of course, there's unknowns about the reactor design. So in our lab, we are actually developing a small scale system to demonstrate and towards the commercialization. This is something we are doing and supported by Queen's University commercialization team.
Great. There's obviously a lot more to this than we could talk about here, but it's very interesting to hear about this progress. Thanks a lot.
Thanks, Robert.
There's a lot of technical details you need to consider when you're trying to put two different processes together at the same time. Just one quick question about the regeneration of the catalyst. My understanding is that because the conversion product is also a gas, it flows it out. So does it involve the regeneration of sorbent at all?
And the regeneration of sorbent and the conversion of CO2, actually, it happens simultaneously.
It's because CO2 is converted into a gas product, which
Yes.
flows out.
Yes.
So basically the conversion reaction takes CO2 out.
Yes. So it's also a regeneration of the solvent.
Right, because it's done under hydrogen atmosphere.
Yes.
It's like we're doing a regeneration of the glove box. That's a very smart idea. Interesting. And the catalyst. So in your presentation, most of the catalysts are kind of established. Are you trying to develop new catalysts, or you're still looking at optimizing the established catalysts?
That's a good point. So for the reverse water gas shift reaction, ICCU reverse gas shift reaction, I think just to personal idea, I think there's no need to develop new catalyst, because the calcium oxide alone, the limestone, the marlstone, already works perfectly. Mm-hmm. So very cheap and very high conversion. So I think that's it. What needs to be done is, as we discussed, how we scale it up, how we make it continuously. And also, the key thing is that one of the disadvantages is the high temperature. So we need a 700 degrees C high temperature. So that's why currently we're working with partners like some companies. We try to reduce the temperature. So in that case, if we want to reduce temperature, we need a new materials, new catalyst. So, yeah.
Speaking to temperature, as I said, it's like doing a regeneration of glove box. But during the regeneration of glove box, the temperature doesn't feel like 700 degrees. It's probably just the, well, theoretically, it should goes up to 300 degrees to regenerate the catalyst for the glove box. Obviously, it's a different
It depends on the material. So we are not only regenerating the catalyst, we also regenerate solvent. So calcium oxide, the conventional calcium looping technology, the regeneration is at around 850 or even 900 degrees, it's even higher. So come back to your question, I think the temperature is mainly dependent on the solvent. If we use a medium temperature solvent like magnesium oxide or even MOF, that means it's room temperature solvent. So then we do the adsorption at room temperature and do the catalysis at high temperature. Then it will change the temperature, but in that case, we'll need a new catalyst.
That makes sense, because glove box regeneration doesn't involve any sorbent. It's just the catalyst, yes, which is copper. You basically reduce copper oxide back to copper, which doesn't need a high temperature.
Yes, there's two things. So solvent, we need to consider catalyst and solvent.
Yes, yes. As I said, when you put two processes together, there's more technical details to consider.
Yeah, a lot of unknowns, and I think I'm happy that there are more and more people actually working in this area now.
It's a very, as I said, it's a very smart idea, and it's not actually a difficult process to understand. No. On paper, obviously, there's details to understand, but on paper, the process, the concept is very easy to be accepted to a general audience. Everyone here, I'm sure, understands this concept. Great. Does anyone have any further questions to our speaker? Well, if no, let me stop the recording first.